Is there anything about 2.6 that's confusing you that you can't get started on the problem? You don't know how to get started on the problem. I mean, is it anything more specific than that? Okay, if I recall, 2.6 has a problem that says if you have something and it decomposes into these two things, then how much of those two things would you need to make the original powder? I think that's the way the question's phrased. And what they're doing there is they're letting you know that it didn't strike me until after I put the slide together that they're talking about both a decomposition reaction and a formation reaction. Basically what it's saying is if you have this structure, if you have all these pieces in this compound and you're breaking the compound down and it forms these elements, you can say, well, whatever it breaks down to, that's what was needed to make it in the first place. So the reaction can go both ways. I can take a molecule, break it down into atoms, which is taking this compound, breaking it down into elements. But then I can also take those elements and through another reaction put them back together again to make what I originally had. So when the problem says you have this compound, you have this substance, and you break it down into these components, how much of those components do you need to make that substance? The reaction can go both ways. Does that help? I'll get the Duplos. Just in case. We'll go over it. We'll go over 2.6 in just a moment. We're going to do a quick review. These things are fun, but occasionally get loose and I drop them and they're kind of a pain. So I'll get to some page in my book, basically, and we'll go from there. Real quick review. Compounds. We talked about compounds and that compounds are substances that can be decomposed into elements by chemical means. And that all matter comes in two forms, either elements or compounds. Now, again, this is it wouldn't necessarily be like this in nature. You've got element blue, element red, element yellow, element green. In real life, these colors would all be scattered together. But for time, I'm going to keep it like this, like it's banded. So this is your original compound, right? It's a substance that it can be decomposed into elements, meaning when I have this compound of 3 blue, 3 red, 2 yellow, 2 green, and I break it apart, that's what decomposition is in chemistry, I break it apart, I suddenly have a bunch of greens, and the greens can't break down into anything else. They're green. There's no other banding, no other colors, no other elements. They're green elements. I can't get any less than green. And same thing with yellow. Yellows can't break down. Green here, you guys that know your art, I can't break that down into yellow and blue. It's not the same thing, right? And reds, I get all the reds together, I get all the blues together. Now, compounds, I said on the slide yesterday, you can think of it in two ways. A compound is something that can be broken down into elements, or you can think of it as a compound as something that takes multiple elements to form a compound. You can build it back up again, okay? Works both ways. Now, there is a little nuance of difference. Sometimes you hear me say elements, and sometimes you hear me say atoms. Sometimes you might hear me use molecules, and you hear me say compounds. It's the difference between the type and the structure. We talk about element. We've already studied a little bit about the periodic table, that every square on there has a symbol. That symbol represents an element. What the element means is that is the substance that I can't break it down into anything other than the element itself. No other elements make up an element. It's the smallest individual unit. And elements are in the form of atoms. One piece, the smallest piece of an element, is known as an atom. And if I have an atom of red, and an atom of red, and an atom of red, I could say I've got 3 atoms of the element red. But normally we have it as a pile, as more than one atom. We can't separate one atom. We'll have a bazillions, and that's a technical term, bazillions of atoms, okay, in our hand. When we have a little bit of powder, we've got bazillions of atoms. Well, when I have all of the elements, or all of the pieces in my hand are the same element, or the same atoms, same structures, then I have the element. I have the element red, and the element red is made up of red atoms. So the atom is describing the smallest piece. The element is its identifier, and usually it's in a group of others that are exactly like it. Okay? So that's a little bit different. You hear me say, okay, we have an element. That means we've got a particular type. If I say I have an atom, I have one piece of that element, the smallest piece that I can have. Now, on a compound, let's say we're using H2O, and hypothetically, red here is my hydrogen and yellow is my oxygen. So here I have the compound of H2O. For symmetry, God/nature like symmetry, so I'll do it like that. Okay? I could say this is red 2 yellow. 2 reds, 1 yellow makes red 2 yellow. Same way that if these were hydrogens and this was oxygen, it'd be H2O. I have one molecule. My smallest structure, my smallest structure of my, in this case, hydrogen, is a hydrogen atom. My smallest structure of the compound, water, is a water molecule. When I say I have a molecule, what I'm signifying is that can be broken down into elements because it's a molecule that is the smallest structure of a compound. We generally don't talk about one water molecule. We talk about a container that has water molecules in it. Okay? So again, the difference between element and atom, the difference between compound and molecule. An atom is the smallest structure of an element. Atoms of that element together is the identifier, but we have, in this case, a compound. A compound is made up of elements. And the smallest structure of a compound is a molecule. Okay. So, elements. What is the smallest structure? If I say I have an element, and I'm looking at the structures of the pieces, and I'll say this at times we go into Miss Frizzle's school bus and go, so when I say let's go with Frizzle, what I'm talking about is, Magic School Bus. You guys are all familiar, right? Okay, so when I say if we were on Frizzle's bus and we went down to the molecular level, what would we see? If we were looking at elements, we would see individual atoms. Because elements cannot be broken down any farther, and the smallest piece, as we understand it, is the atom. So if we're looking at the element hydrogen, we would have multiple atoms of hydrogen. And if we were looking at, from Frizzle's school bus, if we were looking at water, we were looking at the compound water, and compound is made out of a molecule, and we're looking at multiple molecules of the compound water. Okay? Does that help? Between an atom and a molecule. Atoms are associated with elements. Molecules are associated with compounds, because a compound is made up of more than one element. All right. I will assume that the general bobble yes from some of you and the general no response from the rest of you is a general yes. And we'll move on. That might be a bad assumption on my part, but here we go. Now, we talked about the law of definite proportions, and that the proportion of elements in any compound is always the same. What does that look like? Well, we're talking about mass now, and to kind of think ahead, later on we're not going to be talking about mass, we're going to talk about individual pieces. Okay? So let's say we had a marble collection, right? And we wanted to know how many marbles. And we said, okay, for every red marble, I have a green marble. Okay? We make an association with pieces. We can also make an association with masses. If they're different sizes, they have different masses. We can relate counts to mass and back and forth. Right now, we're talking about masses. The truth of the matter is, later on, we're going to realize that a mass of something is a general way to figure out how many of them we actually have. And in the future, we're not going to be so much concerned about how many grams of carbon we have. We're going to be concerned about how many atoms of carbon we have. And so the math gets really big by using Avogadro's number, 6.02 times 10 to the 23rd. It's a big number. That's why when I say bazillions, that's like times 10 to the 23rd. It's a big, big number. Okay, So this law of definite proportion said that in this example, this is what we did yesterday. We had 24 grams of carbon and 8.08 grams of hydrogen, and that forms natural gas. Right now, you don't need to worry about the chemical formula. But we said, okay, if that much mass of carbon and that much gas of hydrogen come together, what must be the mass of the natural gas we make? And by the law of mass conservation, we go through and say it's 32.1 grams of natural gas. Again, we're smart enough now that we do addition, and in addition, we know we can only be as precise as the least precise. The least precise is to the tenths place, so our number becomes 32.1, and we recognize that it involves a little bit of rounding, but it's more appropriate than not rounding it, okay? Because we're bringing more significance to this number than may be necessary, based upon this being only precise to the tenths place. But the big picture here is that whatever the mass of my reactants is, that's going to equal the mass of my products. However much stuff I put in, that's how much stuff I'm going to get out. That's the basic principle, law of mass conservation. But I was told that this is my perfect recipe, right? Remember, again, in chemistry, if you do the recipe wrong, you get out what the perfect recipe should have created, plus your leftovers on top. So when you put the extra egg in the cake batter, you get a perfect cake and you get an egg on top. It kicks out what it doesn't need, what it doesn't use. In this case, they're telling you the perfect recipe to make 32.1 grams of natural gas. That perfect recipe comes from adding 24.0 grams of carbon to 8.08 grams of hydrogen. And when you do that, you will get 32.1 grams of natural gas and no extra carbon and no extra hydrogen. That's the perfect recipe for that much. We good so far? Okay. So 24 and 8.08, that's the perfect recipe for this much, but we don't want this much. We've been asked to create this much. And so, again, using the easy analogy, we've been given the recipe for a dozen, but we haven't been asked for 1 dozen. We've been asked for, actually we find out we've been asked for 4 dozen. Because we have a perfect recipe that'll give us 32.1, we've been asked for 128.4, and so we figure out how many batches we need by dividing what we need, divide that by what the recipe will give us. And that tells us how many times we have to use that recipe. So our multiplier here is 4.00. Again, 4 sig figs, 3 sig figs, division, least sig figs, 3 sig figs. So we need to make 4 batches of the recipe that gives us 32.1 in order to get the 128.4 that we've been required to make. So 4.00 times 24.0 gives us 96.0, and 4.00 times 8.08 gives us 32.3 grams, and that produces 128.4 grams. And we recognized yesterday that this plus this doesn't exactly equal that, but that's all built into the sig fig precision stuff we've already looked into. So this is correct. That's how we figured out from this perfect recipe that makes this much, how many batches we need to create a formula that gives us the amount we've been required to produce. Now 2.6, which I asked you to do during bell work, says that we have 60 grams of this powder, and that 60 grams of powder breaks into 32.8 grams of chlorine and an unknown mass of cobalt. Now, how much cobalt must have been produced? Or how much cobalt was produced in the decomposition of that powder? Yes, sir. Close. Right? 27.2. Am I right or are you right?
You're right.
Okay. Just making sure, because I make mistakes all the time. Okay? I would not get 100 in this course. Because it's hard, because it's easy to make little tiny stupid mistakes, and I do it all the time. So keep checking me. But 32.8 plus 27.2, how did I get that? Remember, my law of mass conservation tells me if I had 60 grams to start with, I have to have 60 grams to end with. My 60 to start is made up of 28 or 32.8 plus some other amount. That some other amount is the difference between 60 and 32.8, which is 27.2. So I have 27.2 grams of cobalt and 32.8 grams of chlorine. And this is the part in your book that wasn't clear, maybe not clear to you at this point, but it's the reversibility of a reaction. If I have this, and through, I think in your book they say words like under appropriate conditions, it means there's a reaction. Whether we add energy to it, pressure to it, whatever it takes, don't worry about what it takes. But if I have 60 grams of powder and I can produce, by decomposing it, by taking it apart, I can produce these two elements, then I can create the right conditions where I can take these two elements and smash them back together and remake the powder. Because I'm transferring the form back and forth. I'm not losing or making anything. I'm just rearranging it back and forth. So if the powder, that much powder can become that much in elements, then that much of the elements can be used to make that much powder. And again, that's a new concept that you may not have picked up on. But now, they say we don't want to make 60 grams of powder, we want to make 2.00 kilograms of the powder. And again, this isn't on your own, which means the answer's in your book, so don't stress about copying everything down perfectly. You need to make 2 kilograms of the powder. So what are we going to do next? Ma'am? Okay, we can do convert kilograms to grams. Basically, I didn't do that as a separate step. But that's true. We would have to relate grams to grams, right? Because we have a recipe that makes something in grams, so we have to convert 2.00 kilograms to grams in order to divide to get what kind of a unit for our multiplier? What's the unit on that thing? Do you remember? Like the last one is 4.00. What were the units? There are no units. Correct. So you've got to divide a unit by a unit so they cancel perfectly. If we divide kilograms by grams, it's going to have a derived unit of kilograms per gram. Okay? So we have to have the same units. So correct, we're going to have to go from 2 kilograms to grams and then divide that by the 60. Okay? So 33 and a third, and everybody knows about the magic 33 and a third is really 33.33333333. It just goes on forever. And you could write it forever if you want to, but you will never do anything else the rest of your life than write that answer. Or you could say, you know what? 3 sig figs, 3 sig figs, 3 sig figs, we're done. See, sig figs just preserve the rest of your life. Or you would have failed the problem. See, so they're good for us. So we're going to make 33.3 batches of the original recipe. Don't think KFC, okay? 33 1/3 batches of the original 60-gram powder recipe. So when we do that, we multiply the original recipe that we have by 33.3 in every instance. And the result is 1,090 grams of chlorine and 906 grams of cobalt. When they are brought together under the correct conditions, produce 2 kilograms of the powder. So while this might sound really scary now because I'm talking chlorine, cobalt, and reversible reactions and things like that, it comes down to, okay, if you have a recipe for 12 muffins and you want to make 30 muffins, how many batches do you need to make? 2.5. So whatever the recipe was, multiply it by 2.5. That's really all this is teaching. And that's a review from what we did yesterday. So let's move on to the law of multiple proportions. We take it one more step. Definite proportion says this and this produces this. I can have a definite proportion. I can multiply it by 2, multiply it by 5, multiply it by 10, and I will get everything as a multiple of whatever my multiplier is. The law of multiple proportions here, though, says that if 2 elements combine to form different compounds, here's the key. If 2 elements combine to form different compounds, it can happen. And the example we're going to use, carbon and oxygen are combined, but you can get more than one product from that reaction. And this definition is in your book. That if 2 elements combine to form different compounds, the ratio of masses of the second element that react with the fixed mass of the first element will be a simple whole number ratio. I know you've already got that memorized because you're hard chargers, we've already memorized ahead. However, what does that really mean? Now, I don't want you to focus on the fact that they say the first versus the second, because a lot of students will get hung up on that. Well, what is the first element versus the second element, and how does that relate to the... Okay, I'd rather you thought of it more in terms of any element, because we can write the reaction and put where we're at in this course, you can put any element first. So like those last reactions, when I had so much chlorine and so much cobalt, it could have been written so much cobalt and so much chlorine. It doesn't matter. So I can put whatever element I want first in that reaction. And what this is saying is not so much about the first element and the second element, is that an element in the reaction, the amount of it doesn't change. But the other elements in the reaction, the amount does change. And if they produce something, they're going to produce something different. And when they produce something, that element which is not the same, we're going to create whole number multiples. And it's easier to visualize when we do an example. So the first example, again, using carbon and oxygen. We're going to look at this product, carbon dioxide, all the time. What do you know about carbon dioxide? CO2, carbon. You're going to know by the end, in a couple days, that that is carbon dioxide. The 2 means, there are 2 of them. The prefix for 2 is di, so it's carbon dioxide. In this room, we have major producers of carbon dioxide. All y'all produce carbon dioxide all the time. Your body is an engine. You've got combustion going on in your body. The fuel that you eat ignites with the oxygen you breathe and produces a waste product of carbon dioxide, and you breathe it out. So your body is continually converting fuel with energy through heat to carbon dioxide, and you're breathing it out. And 12 grams of carbon combined with 32 grams of oxygen will produce 44 grams of carbon dioxide. However, there's another gas that's made up of both carbon and oxygen, and that's carbon monoxide. Mon meaning mono, carbon monoxide. Monoxide means 1. So 1 carbon, 1 oxide, carbon monoxide. If you told me, hey, Mr. Baker, I did a reaction, I took some carbon, some oxygen, I put it together, and they reacted. I go, what did they produce? And you're going, well, they produce the molecule that comes from mixing carbon and oxygen. I'll go, there's more than 1. There are 2. Which one was it? I don't know. Okay. Notice the difference here. 12 grams of carbon and 16 grams of oxygen produce 28 grams of carbon dioxide. Both of them conform to the law of mass conservation. 12.0, 32.0, 44.0, cool. 12, 16, 28, cool. They're both legitimate law of mass conservation. But notice that the amounts are different, but the products are different too. What do we produce? Something different. How much does it take? It takes something different. The law of multiple proportion says if you take the same elements and create different molecules, okay, and if one of those is kept constant, in this case, carbon, the first, the way the definition is written in the book, the first one would be carbon. If that one's kept the same, then the ratio of the second ones are going to be a whole number ratios. Look at the masses of oxygen. Since these are the same, what's the ratio between 32 and 16? Well, it's 32 to 16, which reduces down to 2 to 1. It's a whole number ratio. It's not going to be 1.5 to 1. It's always going to be a whole number ratio. Okay? This is important because we're going to talk about Dalton's theory of matter, and this plays into it significantly. 32 grams of oxygen in the first formula, 16 grams of oxygen in the second formula. 32 to 16 is a ratio of 32 to 16, which reduces to 2 to 1. Whole number ratios. Second example, methane. We make methane, it's a combination of carbons and hydrogens. And the perfect recipe for methane, 36 grams of carbon and 12 grams of hydrogen produces 48 grams of methane. That's a perfect formula. We can also make propane. It's a different combination of carbons and hydrogens. There are lots of carbon and hydrogen chains that we can make. These are just 2 of them. But it's 36 grams of carbon and 8 grams of hydrogen. So which element was kept the same in these 2 measures? They just happen to give you 2 perfect recipes that have the same amount of carbon. You see that? Since the amount of carbon here is the same, what we're looking at is what are the relationships between the other element which was not the same. And in this case, it's the hydrogen. What's their relationship? 12 to 8. 12 to 8. And 12 to 8 reduces down to 3 to 2. And so just by observing this, just by looking at this, sit there and go, this idea that when you have different recipes where one element is kept the same by mass and the other element is different by mass, and they produce different products, that they all are appropriate because they conserve the conservation of mass is there, that the element that changes by whole number ratios. And what that tells us is part of Dalton's law, and so rather than tell you now, I'll just put it in the context of Dalton's law. Dalton's atomic theory, good-looking guy, right? John Dalton. And Dalton's theory. Now, here's the deal about Dalton's theory. It was presented in the early 1800s, and it was given as what did we say about a theory? Is this theory the same as a law? No. A theory and basically what happened is, here's some assumptions that Dalton said. Think of it this way. We can't prove them, but if we assume them, it makes sense out of a lot of stuff. Okay? Let's think of something comical, something really silly, like, something that we would not necessarily do, like maybe some of you are flat earth people, okay? Different theories about reality that are different from other folks. Let's say that you're one of those people that think there's no such thing as chance, everything is due to leprechauns, okay? And you go, wait a minute, I was in my room and it was nice and neat because that's the way I leave it. I leave the room and I come back and it's a mess. Oh, it's the leprechauns. You go, what? I say, well, I can't prove they're real because they're savvy. They hear us coming, they hide. I've never seen one. I can't prove they're there, but you know what? It sure makes what happens in my room make sense. So let's just pretend for a while that there is such a thing as leprechauns. And we'll, and that you get that kind of thinking going. Now that sounds stupid, crazy. It's supposed to be comical, but here's the deal. Dalton said, I can't prove any of this stuff, but you know what? If this is true, it helps us make sense of a lot of things. So let's hear what he said. Let's pretend they're true. And it's much more reasonable than leprechauns, trust me. Here we go. First, he says that all elements are composed of small individual particles called atoms. These are in your book, again. So you can see it on the video. It's here on the PowerPoint. It's in your book. It's in blue in your book. I think all 4 of them are. So you have that. All elements are composed of small individual particles called atoms. Where did he get this idea from? Okay, it wasn't Aristotle. Democritus, right? Wasn't Democritus the guy that says, you know what, as I walk up to the beach, it looks like solid beachness, but as I look at it, it's small particles that make up the beach, and it's not all beach particles, it's various particles that look like one particle from a distance, but as I break it down, they're actually smaller pieces, but at some point, I can't break it down anymore. He just accepted some Greek philosophy here and said, you know what, everything is made up of little particles that can't break down anymore called atoms. Prove it. Can't. Let's assume it and see if it answers some questions. Okay. Second one. All atoms of the same element have exactly the same properties. He said, you know what? When I have my little structure here and I pull out a couple of atoms, and I've got 2 red atoms here. I've got the element red, and I've got 2 structures, 2 atoms of red. You know what? When I take these things, I look at them, there's no difference. They're exactly the same. It's not like this red atom grew up in the north and this red atom grew up in the south and they have different accents, but they speak English. No. Like, these are exactly the same. If you've got one red, you get another red, no difference. They behave exactly the same. They all behave perfectly red. That atoms from different elements behave differently. So you know what? If rather than having 2 reds, I have a red and a yellow, they're not going to behave the same because they're different. Even if they grew up in the same part of the country, they're different. They can't, They're fundamentally different. They're both northerners, but red boy, yellow girl. They're different. There's nothing, they're going to behave differently. They're going to be differently. They're structured differently. So his third point was, hey, everything that's identical behaves identically. And things that aren't identical, they don't behave identically. And the last point, which has to go on another slide because there's just not room, is this idea that compounds are formed when atoms join together. He said we get this stuff, this complex stuff, because simple stuff comes together and makes it. But since these pieces are indivisible, they have to come together all or nothing. You know, let's say we're trying to make H2O, and we've got HO, which would be the Christmas molecule, right? Ho, ho, ho. So we got HO, and we've got another H that's coming nearby, and we're going to make H2O, okay? It can't decide, you know what, I don't want a whole one, I only want half of you. Let's break you in half and only take half of you, right? It can't do that, because this hydrogen is indivisible. Here's the deal. You want to have a relationship? All or nothing, man. You're either all in or you stay away. And that's what this last point says. When compounds form, they take either the whole atom or none of the atom. They can't just take part of the atom. Right? Because again, if the atom is indivisible, you can't break it up to make stuff. You got to take it all or nothing. So, again, he couldn't prove any of this, but it explained a lot of things. Here's the quick summary, the way I would put it in my notes. Everything is made out of atoms, and atoms can't be broken into anything else. If you've got the same elements, they got the same properties. If you've got different elements, they've got different properties, and compounds come from putting pieces together, all or nothing. Here's the deal. If we presume that's to be true, what does it prove? Well, it explains the law of mass conservation. Because if I can't break it up, I can't destroy it. It's all got to be there. So nothing disappears and nothing is created. Therefore, the law of mass conservation makes sense. And it explains the law of definite proportions. Because if I'm making the same thing, it's going to behave the same way. And again, I can't take a half of an atom or part of an atom. And here was the big deal. It predicted the law of multiple proportions. That was proven later. See, when Dalton did this and he came up with this idea, he said it explains mass conservation, it explains proportions, definite proportions, and you know what? I think this is what we're going to find. We're going to find what we just discussed as the law of multiple proportions. He hypothesized it before they proved it. And so when we have a theory that both explains what you see and predicts what you will see, it gives us some real beef, right? It makes it like, I'm not going to say it proves it, but it shows that it's there's some significant truth behind it. And so Dalton's law of atomic theory, this is the background of how we understand matter today. All this stuff that Dalton said. And again, because he explained this, but then he predicted multiple proportions. He predicted that, hey, if you got carbon and oxygen and it makes CO2, and you have carbon and oxygen and it makes CO, that there's a relationship, a whole number ratio. Because it would be a whole number ratio if you can't break up the elements, but it would be a partial ratio if you could. And he said you can't, because you have an indivisible atom as the fundamental building block. So, here's a picture. It's not the same picture that's in your book, but it's a similar picture looking at atoms. Now, when you see a picture from an electron microscope like this, it's a tunneling electron microscope, a lot of people assume that what they're looking at is atoms. And they make a big point about this in the book, so I want to go over it a little bit. But here's the deal. Did Dalton prove that atoms existed? Yes or no? No. Dalton did not prove they existed. Dalton said, hey, come along with me. Let's assume they exist. Let's assume they're not divisible. Let's assume these four things. And oh, by the way, if we assume these four things, everything starts to make sense. But he didn't prove them. He said, let's assume them. So we have a picture like this from an electron telescope that shows us what we would say represent individual atoms. See how they're all lined up nice and neat and organized? And they kind of they look a lot like you would anticipate they would look based upon Dalton's theory. But part of the difficulty here is that's an image, not a picture. What's the difference between, what's a picture? Think about how do you get a picture? You got some film, right? You got something that's going to capture something. And then light comes and bounces off something. I see you because light is reflecting off of you, right? This isn't a picture in the sense we think of a picture. This is an image. And the way you come up with this image is you have this probe that comes really close to the metal, in this case, and it moves across the metal, and it sends electrical current down, and it receives electrical current back, and it has an algorithm in a computer that hypothesizes what should be happening and then creates an image of it based upon the flux in the current. Okay? So when we see a picture like this from an electron microscope, you're not looking at a picture. What you're looking at is a computer representation that explains the changes in the electrical waves based upon a theory. What if the theory's wrong? Does it look like that? This is a physical representation of a theory, not a physical representation of absolute reality. And there's a difference. Okay. Say right now, we can't prove that atoms exist. We assume they do because they explain so much. But if it came right down to it, we've never been able to prove that they actually exist. So I hope that doesn't undermine your whole sense of, well, why are we taking a class that's based upon fiction? Well, it's not. It's based upon truth, but maybe not in the same way that we commonly understand it. And we'll talk later, too, about models and what it means to be a model. And again, we're not talking about keeping your feet in a straight line and doing the stupid wiggle as you go down the runway. Models in here are ways to explain reality, and that's not reality, okay? Models are ways of explaining reality, and they're not definitively true. We just had a hurricane, right? What's the hurricane? Where's the hurricane going to go? Well, based upon the 5 most accurate models, we have the storm tracking in these 5 different paths. They took the models that tended to be the most accurate, and they put the 5 of them together, and they came up with 5 different answers, and they took the average of the 5 different answers. Why? Because we don't understand all the variables of a hurricane. We cannot predict exactly where it's going to go and what it's going to do. But we've got models which are different, but they're all very close. So we say if we take the average of the close ones, we should be closer to be able to predict what will be true. So Dalton's theory has a few little things about it that we're going to push against, though. Okay, Dalton's 4 points, right? But 2 of them are not completely accurate. And I've already kind of inferred this already. 2 of them are not completely accurate. Dalton said that all elements are composed of small individual particles called atoms. And I've said this many times. Yeah, that's true, but we can split the atom. Okay. Now, we're going to say this several times throughout the year, but it's beyond the scope of this course. We're not going to be splitting any atoms in here. Okay? And when you get to splitting the atom, you're talking quantum physics and all this kind of stuff. We're talking more about the physics class, but physics like we do here on steroids, way beyond what they'll ever even think about. So when it comes to splitting the atom, we're not going there for our purposes. We're going to assume Dalton is true because everything we're going to do maintains the integrity of the atom. So though we know we can split the atom, we're not going to do it. We're going to keep whole atoms together in this class. And second, that all atoms of the same element have exactly the same properties. When we get into the makeup of the individual atom, we're going to realize that there are some neutral particles, okay, the neutrons in the nucleus, and that atoms of the same element can have varying numbers of neutrons. So they're not exactly identical. Every atom of cobalt is not necessarily exactly the same. It's going to have exactly the same number of protons. It's going to have exactly the same number of electrons when it's in a neutral state, but they're not going to necessarily have the same number of neutrons. They're going to form isotopes. And we'll talk about that later. So except for those 2 caveats, everything else from Dalton appears to be accurate. Therefore, Dalton appears to be correct, and it appears to be true. And we're going to use those assumptions for the rest of this class. Any questions for me? Tables 2.1, 2.2, and 2.3. In your book, if you've read that far, you just have to have them memorized. they're going to become very important in the next couple days when we start talking about naming compounds and how we determine the names of compounds. This may be pushed out a little bit depending on how quickly you go through the material. But everything in review questions for Thursday we've covered in class. Table 2.1, I believe that is the IDE names of the elements. Don't worry about exactly what that means right now. You need to just start working on memorizing the table. That table is on, let me see, go ahead. I passed it. Table 2.1 and 2.2 are both on page 67. Table 2.1, the IDE names of nonmetals. You know, what is that? Right now, don't worry about it. Just be able to see, if you see an H, know that that's hydrogen and its IDE name is hydride. H is hydride, C is carbide, N is nitride, O is oxide, F is fluoride. There are 10 of them. 10 symbols and 10 IDE names. Table 2.2 are the prefixes. So when you see mono means 1, di means 2, tri means 3, tetra means 4, penta means 5. It goes from 1 to 10. So anticipate on Thursday a quiz on the IDE names, on Friday a quiz on the prefixes, and on Monday, that's the one you should have been working on already that I told you about last week. Table 2.3 is back on page 77. Those elements whose names are in bold, you just have to memorize them. To know that, for example, helium is a symbol HE. Sir?
Work on Friday, do you need practice problems 1 through 10, or just 10?
Typo, yeah. Practice problems 6 through 10. Yeah, practice problems 6 through 10. 1 through 5 is Thursday, so that'd be 6 through 10. Actually, review question number 3, we didn't do the lab in here, so you can skip number 3. It takes you back to the lab, and you could read the lab, but don't invest that time right now. So for Thursday, it's 1, 2, 4 through 7. Okay, skip number 3. So again, going back to table 2.3, the bold names, know the symbol and be able to write the name as well. You should be able to go both ways on that chart. So nitrogen is N. If on the quiz you're asked, what's the symbol for nitrogen, you would write N. Or if asked, what element is represented by the symbol N, you would write nitrogen. So this is one of those things with these 3 tables where there's no brain work to work around it to figure out an algorithm to give you the right answer. You just have to memorize it. This is a case where flashcards would be key, I think. This is the way I would do it. Flashcards for the names, flashcards for the element symbol, 1 on each side. Work it from the name, check yourself to know the symbol, then work it from the symbol, check yourself to know the name, get with a peer, review it, rehearse it. So there are 10 for memorize on table 2.1, 10 for memorize on table 2.2, and I think there were probably 20 or so on table 2.3 for Monday. The stuff that is going to be due on Friday, we should be able to get through that whole content tomorrow. And so that's why I say we may push it back depending upon what we get to. So if you work ahead, or if you've already been doing it, just look at the problems in the book, and if we've already covered that content, go ahead and do it. Because you'll be expected to be able to do whatever we at least covered the day before in class.